Hello, this is the last example of this slide. We are going to use the overbooking example that we used in chapter 5. So this was one of the examples I considered in chapter 5, binomial distribution, but now I increased the scale. At that time, we could not calculate such a big number, but now so at that time, I remember we considered like 20, number 20, like a bus, anyhow. So consider an airline accepts overbooking. So it accepted 400 reservations for a flight, but the flight can accept only up to 370 passengers. There are only 370 seats in the flight, but the airline already sold more tickets. And it's because there is a probability of cancellation, and which is 10%. And as before, I'm going to assume that the reservations are independent across each other, and the probability is the same. So these assumptions are hidden. Let me proceed without saying that. And we are particularly interested. So the airline sold 30 tickets more than it can accept. So 30 tickets are overbooked. It means if the cancellations number of cancellations is 30 or fewer, then overbooking causes troubles. So if only, let's say, for example, if 20 tickets are canceled, then there are 10 more passengers who need to take the flight than the capacity of the flight. So then the first method, so we are going to calculate this probability. And the first way to calculate that probability is to use the binomial distribution. So as before, we define y as the number of cancellations. Then we know that y follows a binomial distribution with parameters 400 and 10%. So 400 is the number of reservations, or this is the maximum number of cancellations, and 10% is the probability of success. Here the success is cancellation. So probability of cancellation 10%. And we need to calculate this probability. Here it's not easy actually. In chapter 5, I told you that to calculate this probability, you have to calculate probability y equals to 0, y equals to 1, y equals to 2, and you have to sum those probabilities up to 30. So you have to calculate 31 probabilities and sum them, which is not easy. And each of the probability is also very complicated because the number itself is 400. So if you think about the combination rule, you have to choose 30 out of 400. So you have to multiply a lot of numbers. That is very annoying and very complicated. Of course, it's not a big problem to a computer. Computer can do this like in this like just at a blink. So anyhow, I used Excel and I got 5.239%. And this is not an approximation. This is it's an approximation in the sense that I rounded the decimal place at the third decimal place, but the probability itself is not an approximation. This is the first approach to calculate this probability. And the second approach is to use the sampling distribution for the average. And so now what we need to convert the binomial random variable into the average. So we are interested in probability binomial smaller than 30, and when you divide both sides by n, which is 400, you will get this probability. So it's the same probability. I just divide both sides by the same number. So we are going to calculate this. And as usual, to do this, we have to obtain the mean and the standard deviation of x bar, because we need them to standardize this probability. We have to make this probability to a standard normal distribution. And to get the mean and the standard deviation of x bar, we need to know the mean and the variance of a single observation. And in this case, the single observation, a single outcome is a binary variable. That's the assumption. Or in our example, it's cancellation or not. So cancellation is 1 and non-cancellation is 0. So you know the probability. It is a simple binary distribution whose mean and standard deviation is well known. We learned it in chapter 5. The mean equals the probability of success, which is 0.1. And remember, the variance was probability of success times probability of failure, which is 0.09. And it's a nice number because when you take the square root, you get 0.3. So standard deviation of a single binary variable is 0.3. Mean is 0.1. So using these two values, we have the mean and the standard deviation of the average. The mean is the same as the binary random variable, and the standard deviation is standard deviation of x bar is the original standard deviation divided by the square root of the sample size. In this case, n was 400, so it's simple algebra. Then finally, the center limit theorem implies x bar is normally distributed with mean and standard deviation. So just use those two numbers in the standardization. You get probability z, the standard normal distribution, smaller than minus 1.667. If you just calculate this, it is minus 1.667, and then you get 4.779%, right? Okay, I think I did it too fast. So let me repeat. So we wanted to calculate the probability that the number of cancellation is 30 or fewer. So this is the number of cancellations. But when I write it this way, it means that the percentage of canceled reservations is less than 7.5%. So this is the average, which has to be interpreted as a probability. So instead of the number of cancellations, we use the ratio 30 out of 400 equals 7.5%. So the probability of cancellation must be less than 7.5%. And then to calculate this probability, we need the mean and the standard deviation, and then use them here. Subtract the mean, divide by the standard deviation. Then the 7.5%, the 0.075, is standardized to minus 1.667, right? So on average, 10% is canceled, but you have to have less than 7.5%. So it's a negative number. So as a result, when you put this number into the standard normal distribution CDF on Excel, for example, you get 4.779%. This is the result from the normal distribution approach. Compare them. So basically, we are calculating the same probability, same the probability of the same event, the event that 30 or fewer reservations are cancelled. And when you use the binomial distribution, you got 5.2, but normal distribution yields 4.78%. Their difference is the approximation error. So this 5.239 is the correct probability. This is the true probability. There is no approximation error in the distribution. But this is an approximation using the center limit theorem. So this probability requires that the distribution of x bar is close enough, similar enough to a normal distribution, but it is not. It's not exactly a normal distribution, even though it's very similar to a normal distribution, not exactly a normal. And so the difference is the approximation error, approximation to a normal distribution, and this error is just a matter of convergence. If n, the sample size increases, the approximation will be more accurate. So the approximation error will decrease as the sample size increases. So like, for example, going back to the graph. So as the sample size still this graph started to look like a bell curve normal distribution, but it's not a normal distribution. It looks more like a normal distribution, but not exactly. It looks a little more, even more like a normal distribution, but not exactly. As n increases, in the end, it will be a perfect normal distribution. So any other distributions see a similar pattern. At the beginning, it's never looked like a normal distribution, but as sample size increases, in the end, it is going to be a normal distribution. So that's the approximation error we have and the result. So this is it for this chapter, and today I gave you some time to relax. By the way, I hope as you may know, there were power outage in this area and the Albany and Schenectady area, Clifton Park area. I hope you are safe, and if you have difficulties, please let me know. I understand it's an emergency, so I hope you are doing well. And I'm very sad that my son does not go to school for 2 days. I have to take care of him. That was horrible. Anyhow, see you. Have a great day. Bye.